So hello everyone, today I will present on the topic Cmos in Space, and this is a very interesting topic because it encompasses the development of the entire space industry, how the role of electronics and especially Cmos technology was included within the development of the space technology. This would be a hybrid format of a presentation. I would not just go on with the PPT, I would keep on changing between the slides and some papers, some of the photos, so it would be an interactive session. Please feel free to stop me anywhere in between if you have any doubts. So this is kind of the flow of our presentation. We would start with a brief introduction and then explore the role of CMOS in aerospace industry. That means the space vehicles that take stuff from Earth to space, or orbiters that are moving around in space, satellites, some things that are related to computing. And then we will also have a brief look at the astronomy side of it. So CMOS is a unique equipment in terms of space technology because it is used both in the computing units, the flight computing systems, the main onboard research computers, and also used as a CMOS pixel detector, that is active pixel system that we'll see just now. And what it does is it captures basically the images of the cosmos and then converts it into wavelengths that we can see. So let's take a look at this exciting technology. This is the overview of CMOS. Started in 70s, 80s. The first CMOS transistor was built at the Bell Labs, funded completely by the Bell Labs, and since then many people tried making a lot of variations of the CMOS, and some of them were successful in building quite different interesting applications in different industries. Especially for space, it was the actual development for space-based CMOS transistor was built in 1990s at the JPL lab, funded by NASA. And the first CMOS transistor was actually an active pixel sensor that was used to capture the images on the Galileo spacecraft. Now let's take a look at, so these are just the general things why CMOS is better for space compared to, there were some things called charge capacitive detectors, CCDs, which were used earlier before CMOS technology was there. And what they were essentially chemical strips that captured the different photons of different wavelengths. And due to that chemical reaction, we were able to see the different images. But this process was not very sturdy. It was not very proof from the background radiation. Very easily the images were corrupted. So CMOS was developed keeping this in mind, so that it was radiation proof, smaller in size, and all the different benefits. Let's take a look at, okay, so this is the first CMOS chip that was built for space applications. The person here is Eric Fossum, and he was the developer of this chip along with his team at JBL. As you can see, a lot of different companies after they developed it started replicating the design into modern day digital cameras like Kodak, AT&T, Bell Labs, etc. But the pioneer of the technology, just like many other technologies that we use today, came from NASA itself. Now let's take a brief look at the development of this first CMOS based imaging sensor called Athena. Now I think you should be able to hear the audio, but just a second. Okay, let me start up the video in a different player. Maybe that will work. Yes.
Cameras and image processing have come a long way, and thanks to advanced technology, it happened a lot more quickly just over the past 20 years. During the early 1990s in the General Motion Laboratory, Dr. Eric Fossum and a team investigating new imaging technology that could reduce the size of cameras flying on interplanetary spacecraft.
And we want to have technology that would cost a tremendous amount of money to develop and have a very small camera that didn't consume much power, and also something that we can actually customize for the particular application.
In their research, the team was using complementary metal oxide semiconductor also known as Cmos, which is for microprocessor chips.
We already saw, the ability to put an amplifier in the pixel with the CMOS active pixel type of technology. And of course, too many of the issues that were sort of holding back MOS type devices, it showed that actually you can develop an imager with a very good performance.
This is the imaging module that is
CCD technology and other type of MOS technologies.
And Fossil invented what is now universally known as the active pixel sensor, or APS. While Fossil's team continued to work on the APS, they started a firm called PhotoBit, licensed the technology to an agreement between NASA's Jet Propulsion Laboratory and the California Institute of Technology. PhotoBit improved APS for a variety of applications, from medical imaging to machine vision applications.
so PhotoBit, the parent company, was the one that started actual applications of CMOS sensors and applications on Earth. From X-rays, X-ray was the biggest one, so different satellite imaging, everything.
Application really set things in motion. A number of amazing cell phone
And
manufacturers-
definitely the first cell phone camera that was launched in Japan was actually developed at their lab.
I'm excited about new technologies. Was the first place we started seeing cell phone cameras pop up with CMOS devices.
Meanwhile, in 2001, Micron acquired PhotoBit.
They had
You might have heard of the company
manufacturing
Micron.
capacity
So they acquired
and
the
silicon fabrication
patents and
technology.
everything.
Really
They
taking
won't
a
buy
big
it.
step from being kind of a startup mode to giving us real big scale to address the markets that we're entering into.
More recently, Micron spun off the imaging sector known as Aptia so it could focus on a rapidly growing business and technology. APS continues to progress, keeping pace with advances in the semiconductor industry, which translates into new applications for the future, such as surveillance. Today, no one knows just how far the active pixel sensor can go.
That's the other beauty of the technology. We integrate the analog readout electronics, the analog digital converter, and all the image processing, and are really going to have a true camera quality video or still images off the chip.
So that was a brief story about the first ever CMOS camera or the pixel detector that was made. Let's jump back to the presentation. Okay. So this is the RCA Cosmos. RCA was a company just like Texas Instruments at one point in history, exactly at this point in history. It was going to overtake Texas Instruments, but they took some bad decisions in management and so were not able to come up with it. But this was the first ever chip that was used as a computing system in the aerospace industry. They used this chip to as a part of the main computer on one of the space missions, and what it is actually a combination of two previous versions called CDP 1801 and CDP 18101. And as you can see, some of the familiar terms that you might have come across, like D-register, on-chip clock generator, things that we take for granted were at that time a novelty. And the biggest benefit of it was the CMOS design that it has, and no previous chip ever or any integrated circuit ever had a CMOS design fabricated within it. So this was one of the cool applications that started the trend of Cmos In Space applications. So this is actually that IC zoomed in, and you can see different boards. See if the resolution is not very good, but each one of this is actually a flip-flop. So this image is a crop version, but actually it was even bigger than this. This is the first ever CMOS chip used in space. Okay, now let's talk about the first mission that used it. Same chip, the Galileo. It was really a pioneer in space technology because it was the farthest one at that time that went near the orbit of Jupiter, and also the first one to employ CMOS. The real fear of using CMOS in that time was the volatile memory, because as you might have already learned that CMOS based devices don't actually have permanent memory, at least not at that time. So what they did was build it using some radiation proofing, and there was a little bit of risk, but this is a novel process where you use sapphire as a substrate, and sapphire is just a variation of diamond. So sapphire is so proof against the radiation that it prevents any radiation effects coming onto the CMOS circuit. And it is still used to the day. We'll see modern day sapphire based circuit, but the design and everything that was being done at that time was the first ever application in space. And the same chip that we saw, RC1802, six of them were essentially the only computer that they had on board. The same chip that we saw here, 6 of them were everything that this spacecraft had while going near Jupiter. And we'll soon see where it is right now, because it is still functional. Oh wait, Galileo is not still functional, but still it was functional for 20 to 30 years. So well beyond whatever we had at that time in terms of space technology. It was 8-bit microprocessor, and yeah, just some general details like 16 mega clock, and let's dive deep into that thing. So can anyone say what this number means? Like, how would you read this number? Any idea? Billion, million? What is this number saying? You can count the zeros. If you want to start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So any idea? So this is how many CMOS transistors, a rough estimate that space has right now, in terms of all the satellites, in terms of all the images, in terms of all the flight control systems of the modules taking us to space, especially from SpaceX. And the number counts up to 1.59 trillion. So 1.59 trillion CMOS transistors are currently out of the Earth's orbit. That's a very cool thing to see, because no one else in the universe can actually make CMOS except humans so far. Now this is an upscaled version actually of the image, because this image is so old. It's the Voyager 1 mission taken by NASA scientists when it was being prepared in the clean room, and this is the first ever mission that went interstellar, or at least out of our solar system at that time. So you will see some description here. Let me just put it down. So it has a couple of computing systems, because it was a little bit more complicated space environment, space vehicle. The computer command system was kind of the main computing system that controls everything, and it employed CMOS in terms of constructing the processors, the memory components, and this here is the whole memory main unit of that particular computing system. So what you are seeing here is just a bunch of CMOS transistors used in terms of a flip-flop. And the inbuilt, onboard flight data system was to control everything about the orientation, these gyroscopic effects, and how to set up the reaction wheel, because at the time we are using reaction wheels. And what it used was how CMOS was useful in that was it provided low latency compared to the earlier generation computing devices, and you need faster reactions when you are dealing with aerodynamics and stuff like that. So this is an exhaustive list of all the computers on there. Each single one of them uses CMOS for a particular benefit that CMOS has. You will see the high gain antenna, which was not very successful at deploying, but it had the potential of transmitting communication signals from Jupiter to Earth, which at that time was not possible. And CMOS helped us there because the earlier chips were very high voltage consuming, and compared to them, CMOS used very little voltage, around 10 volts of operational voltage. And so this is kind of our solar system right now, and you can see where Voyager 1 is. The distance is just quite far from us right now. It is the farthest man-made object in space so far. Now let's move on to some recent things. Can anyone say what this is? Does anyone have an idea?
It's not this.
Yeah, but what do you call this kind of thing?
Space shuttle.
Space shuttle, exactly. The next step from just sending random objects, so there is a break in between, because Apollo missions were not conducted using the space shuttles, but Apollo missions in themselves were a miracle because they used just a system of complete NOR gates. That's all their computing system was, just NOR gates, and that's how they built their entire flight computing system, the communication modules, the life-sustaining environment, everything. But talking about CMOS, let's focus on space shuttles. How did the space shuttle program use the CMOS? Now, they didn't have very sophisticated computers even at this time, so what they used CMOS for was to control the vector, the thrust, and also the propellant mixture of this RS based space thrusters. And these are actually space engines that are used to launch the vehicle from Earth to space. How CMOS was used was it replaced the plated wire memory. So earlier, before CMOS, there were plated wire memory, and the problem with them was that when you reach a certain temperature, the data on them is completely destroyed. So, say for example, one of your engine starts malfunctioning in the middle of ascent, then your whole mission is practically compromised. So CMOS was the next best choice, actually the best choice at that time, and that's why since then we have started using CMOS. As I mentioned, the power requirements are way less compared to the previous technologies, so that's also better, because when you are going to space, you always have to be resource efficient. CMOS technology will always be resource efficient because it is smaller in size, it consumes less power, and it's generally faster compared to other technologies. Now let's move on to something even more recent. Can anyone say what this is? ISS? Yes, it's the International Space Station. And to be able to describe how many CMOS are on the ISS is impossible, because they literally have laptops on every single corner of the space station. But the main computing systems are just immensely powerful compared to any space mission before this one. And they were using over the count of around 1.8 billion or something CMOS transistors at the time it was being built. So now with the modules adding up every year and all the repairs and all the new stuff going on, the estimate of the amount of CMOS being used is just immeasurable. Let's switch on to the astronomy side. So at the beginning you saw that the first ever CMOS used in space was for the active pixel sense. And this is especially useful in astronomy because these are all the images that were took with the help of CMOS based sensors. This one has been taken on the JWST space telescope using the NIRCam, which is the near infrared camera, and this is also taken from the JWST space telescope using the same NIRCam, and this is the photo of Saturn in the infrared range. So you will be able to see some bright spots on the ring because methane as generally looks very bright in infrared compared to the normal light where we cannot see. And you can also see the moons of Saturn in this image. So all in all, it's a very good imaging sensor compared to charge coupled devices because CCDs don't have the range of changing their aperture or being able to change, although the newer versions will definitely have aperture control, but technically CCDs only are able to control the exposure based on one single shot, whereas CMOS is just a configuration of multiple CMOS transistors. So how this image is taken, for example, I have a square plate of CMOS just this big, and all the transistors on it, the photons hitting on the transistors are being, it's a grid, so I'm counting where the photons are hit, and based on that grid array, I am able to recreate the images with such a high resolution. So also we have a very important application of CMOS on the Perseverance rover. So they had something called, they simply called it SuperCam because it was just so super. This is the structure of the CMOS in that. There were a couple of analog components and LVCS, low voltage control system, and also this is actually the CMOS pixel sensor that is being used on the rover on Mars. And we'll see a couple of images that it has, but you can see the number of active pixel counters, you can say, that the sensor has. And these are, I mean, the projector is kind of distorting the images, but these are actually at the resolution of 1080 pixels. So we are able to get 1080 pixel images from Mars. How cool is that? This is one of the Ingenuity helicopter that was sent there. This is just the photos of Mars's surface. So, having done all of this, what do you think what would come next? While I said that CMOS technology has been used since 1990s, around 1970s, it has not been used very extensively, especially because the technology that was built on CCDs, the charge coupled devices, was so much advanced compared to CMOS until so far. And in one of the recent meetings that I attended, a workshop from NASA, they confirmed it that in the next missions to come, CMOS would be the main component or the main imaging system on board. And the photos that you saw were in the range of infrared. So just imagine when we have CMOS pixel sensors which are in the range of visible, how beautiful the pictures will get and what kind of information lies there. So this is the future scope of Cmos in Space. So this is currently, you might have heard about this mission, it's called Europa Clipper. So what this spacecraft is going to do is it's going to orbit Jupiter and take images, samples, stay in orbit for a couple of hours every day for the next couple of months to come. And it has a CMOS sensor in it that has a focal length of 1000 millimeter, which is quite high for space applications. Now 152 mm aperture, which means that even in the brightest light or in the darkest environment, it can take good pictures. Also, let's take a look at some of the resolution. So it can have the resolution of 0.5 meters per pixel. Having done work in GIS systems, this is not even equivalent to what we have here on Earth. Because even here on Earth, we can only go as far as 2 meters per pixel. So you can understand the amount of development that has been going on in this Europa Clipper mission and the tremendous technology that's being used in terms of CMOS pixel sensors. Let's look at the next mission. So this is a proposed mission of NASA. It's already ongoing in terms of construction. It's called UX, and it's going to capture the cosmos in terms of UV. And what it's going to use, so this is a proposed version, but what it's going to use are a couple of sensors that are based on CMOS technology, like the near ultraviolet and the far ultraviolet. And what this would do is that so far, in terms of ultraviolet light sensing, we only had CCDs. And they were not able to discern between distance objects because it's, as I said, a strip that just captures the photons hit of it. Once we have CMOS based sensor, we can actually detect each single bit from the CMOS grid. That would give us the ability to discern how far an object is. That's why we have the far and near ultraviolet. When we take the periscopic measure between both of them, we can estimate the distance of a faraway object. So that's the first time that we are using the CMOS. This would be a couple of CMOS transistors that would be used to estimate the distance. So that's the first time we are trying to observe the stereographic effect of space object using CMOS sensors. Yes.
If I'm not wrong, James Webb telescope also uses the UV. So why is NASA sending another one?
James Webb is supposed to expire in the next couple of years. So every telescope has a certain lifespan. We have been extending Hubble for the last 20 years,
Yes.
and it's a very good point that you picked up because in the last 20 years, Hubble telescope was dead, and very recently we switched it back on. Same with the Voyager 1 mission. Let's go back a little bit. So the Voyager 1 mission that I mentioned, this one, is still in active communication with Earth, and see the tremendous power of CMOS. At the time that it was built, it had 6, as I said, the computers, and this one had a couple more. And what we did right now in the April of 2024, because one of the main computers was shut off, we just simply shifted the code from one of the computers to the other one. And CMOS is still going on after so many years. So this is actually the biggest application of CMOS in space. It's longevity, because we have so much development going on in terms of increasing the lifespan of space applications that CMOS is the practical next step. Yeah, that's it. Oh wait, let's talk about what's so special about CMOS in space. So we learned about how CMOS is used, how its history was, but why, and also what its future will be. But why we are using CMOS especially in space? Why not simple IC based circuits? Let me show you. Just a second. So have you ever heard about cosmic ray radiation? So this is Earth's magnetic field saving it from the radiation from sun. And the sun itself is saving us from the radiation coming from cosmic background. So these are high intensity gamma rays that are being thrown not only by the black hole at the center of our Milky Way galaxy, but also coming from faraway galaxies with high intensity gamma particles, which would definitely cook up your electronics, whatever kind of radiation proofing you do. So how do we mitigate these challenges? Using CMOS, we use something called radiation hardening. Radiation hardening is a process in which you, as we saw, one of the applications where the sapphire was used as a substrate to eliminate the incoming gamma particles or any charged particles for that case. Now let's see some of the, okay, let's see at the, so this is something cool that you can say from the manual's cover that it's quite old. This is the first ever CMOS that was made, as you might remember, CP, and they called it Cosmos at the time, the company RC. Just getting a brief understanding of how the design was at that time, you can see some familiar terms like channel, substrates, right, and this is the most familiar structure that you have from this semester, as you can see. So this was actually the first ever CMOS transistor made and in production all over the world. It's quite a lengthy manual, but they have described the use of CMOS. Whatever you have done in your lab files, basically that was the first ever lab manual, the first ever manual of a CMOS transistor. Making NOR gates, making NAND gates, making SRAMs, making flip flops, all of that, making adders. So that's actually the menu of this, saying the time delay, everything. So that's how the first ever CMOS transistor was described. Let's look at something more cool. So how does this concept of using CMOS for observing space particles came from? Using the active pixel sensor. So the concept, as usual, was found from a physicist at the Sun laboratory in Switzerland. And what they did was, while they were performing some particle acceleration experiments, they were able to capture some of the particles onto the cameras, but the cameras were not able to discern between the intensities of the different particles. And so they developed this earlier version of CMOS that was then emulated in space applications as a pixel sensor. And so the idea of using CMOS as a pixel sensor came from here. And you can see that the design of CMOS is already quite different from what you've seen so far. And this is to allow only a fixed part of the pixels to enter the particular sensor. Because what happened is that in that large hadron collider, so many pixels were always hitting each other that it was quite difficult to understand which particle was which. And so you can see, also just look at the voltage range that they are using, it's 100 volts. Because definitely when you're observing particles going at the speed of light and that are highly charged, you have to have some level of saturation within your own circuit to be able to discern between two different levels. And yeah, this is how, so this is the different variations that they suggested should be made within the pixel sensor. You can see different types, different configurations. They not provided a lot of detail, but just say that these are the different variations that could be built for making a pixel sensor. So yeah, this was the one that they did a prototype of. This is the one that the active pixel sensor, the first ever CMOS image camera, was based on. And this is just a couple of, there's a little bit of chemistry here in terms of bonding and what kind of noise effects they have. They are observing different frequency channels along with different materials that they are using to see which material is best for fabricating it, because this was actually the first time, so they would have no idea of what is the most suitable materials. So yeah, that is also something cool. And let's see if we can. So this is one of the research papers that's describing how we are going to use CMOS in future in terms of astronomy. And Can you guys see the images? Yes. So these are some of the, I'll just go briefly over the paper because in depth it's quite out of the scope. What they did was build their own Cmos Space sensors, and what they are doing is, as Aryan said, stacking them in a 3D layer. And how they use the 3D layer is by having more power, they are capturing more and more number of images. And especially if you ever use photography, you would know that the exposure count increases the size exponentially. So what a 3D stack or a higher computing power CMOS allows us to do in terms of space application is it allows us to have longer exposure rates. Now keep in mind that we already have exposure rates on the James Webb Space Telescope as long as 2 days. So for 2 days continuously it's taking a picture of one part of the universe. Now we are able to demonstrate that using the CMOS sensors we can increase it. So just imagine the amount of stuff that you can see in space, so many things that are hidden because the redshift phenomenon, because the intensity of light decreases. So now having more powerful pixel sensors, we will be able to capture even more powerful images. This is one of the prototypes that they made, and this is it in action. This is actually the Astropix, what they call Astropix, the image sensor. The rest of the module is just the surrounding architecture. Let's see if they have a photo of different versions that they did, because they have created a couple of versions. So yeah, as I said, this would be the next version that's going to be employed in this one. And what they are doing is dividing that pixel sensor into 4 different parts and using each one of them for a different application. Because generally, when you're looking at a point in space, you don't actually cover up the whole surface, because if an object is so far away, it's only going to point its light at some part of the image. So why not divide up the pixel sensor? And all of these are connected in a grid. So each one of the pixel can be mapped in terms of the grid address. And what we have on this sides along the cells and rows is a couple of transistors which are activated based on the combination of the row and grid, and based on that we detect which pixel was in. This is the proposed architecture. It's called the U system. So the number of racks that you have, it's called 1U, 2U, 3U, and it's a popular term in satellite in terms of the space that you are going to occupy. So that's the future application of using CMOS based pixel sensors. This is also one of the images of the version that we made. I think it's version 2. Could be. And so as you can see, there are different layers upon layers of the sensors, and yeah, it increases the sensitivity overall. So this in this one. Yeah, so this is just a different version of the CMOS based processor that we saw. Okay, so this one. Okay, this is quite a lengthy one, but here NASA is trying to show us the usage of CMOS in that time. That is such of the part where CMOS is. Okay. So here, as you can see, they are mentioning that CMOS type semiconductor RAM are used in one of the missions that they are doing. And this is at the time of the end of the shuttle era. So you can understand how the whole environment of space was built up from the usage of CMOS. Because at that time, the use of CMOS was new, and everyone wanted to explore this new fancy term. So, yeah. Any more mentions? Okay. So as you can see, how new the term was that even NASA had to demonstrate like what is the full form of CMOS. This is at the time when not a lot of people knew about CMOS. And these are just the index searches. So yeah, that's about a little bit about the history of CMOS. Have you seen this one? So yeah, this is an important one. It's CMB 4000. It's the same one that we used on the Mars rover, the Perseverance rover that and you can actually buy this one off of the internet. So this is as good as that. Now I want you to observe some things on the menu here. especially the voltage rating. So you can see how we started with 10 volts in Cmos technology, and now we are bringing it down to 2 volts, 20 volts, very low power technology, which is essential in space. And the main thing was the temperature gradient. Just a second. So these are the spectral responses. Tells you how good the sensor is at observing each wavelength of the light. You can see, as usual, the the high frequency or shorter wavelength signals have a very small window of capture, whereas signals that have high wavelength or lesser frequency always have a higher window of capture, because your sensor is supposed to capture longer wavelength signals better because it would produce less noise, because higher frequency signals always produce high noise. So that's a cool thing that you can relate with your basic electronics knowledge. Yeah. Let's see. This is just a research paper. So this is one of the student research papers on how radiation hardened CMOS are made. They are describing the chief modes of radiation that any circuit in space faces. They are galactic cosmic radiation coming from the different galaxies and even outside of the galaxy. The solar particle events are quite not that dangerous as long as you are under low Earth orbit or even up till GEO. But once you cross that, you are bombarded by even the alpha particles and the gamma rays from sun itself. And the trap radiation. Trap radiation is something that once a metal particle in a spaceship is hit with gamma ray, the radiation always has a half-life. So it's going to keep on decreasing its half of its substance, but it's never going to completely zero. How do we deal with those residue-based radiation effects? They are not exactly telling us how they mitigated these effects, but this is a good way to understand how different ways of radiation. It's not just like it's radiation, so just put a metal shield over it. There are multiple ways of radiation that can affect the circuit. And for one of the NASA missions, what they did was, even for Europa Clipper, what they are doing is they're just putting all of the electronics in one safe box that they are calling it's an actual down safe box, and they are shielding it with different materials that are bouncing back the gamma rays. So that is one easy solution, but when you are working at the scale of electronics, a couple of things occur. So do they have a description of the troubles that there are? Yes. So what happens if radiation hits your circuit? Let's talk about that. What do you think would happen if high charge particle hit one of the D flip-flops in your phone?
It would change the signal.
It would change the
Signal either zero. It would invert it basically.
Exactly. It's called single latch error.
Yeah.
Single latch errors are still easy to overcome, but when the state changes to completely, it basically completely fries the circuit, then there's nothing that could be done. So single latch errors are the power of a CMOS transistor, because all the other previous transistors didn't have this error detection correction modules within them. They also didn't have the ability to neglect extra power. So CMOS, especially radiation hardened CMOS, are able to sustain errors up to single bits. And sometimes you might have seen these effects, like completely out of random, your laptop or phone starts glitching. Why do you think that that might happen? It could be due to an internal error, or it could be due to a gamma ray hitting it from the space. We can never know. But there have been instances recorded over the internet where completely out of the random, without any internal error, systems have started malfunctioning at the point of single bit. This is most visible in video games, when you are playing a level and then suddenly switch to some other place, because the difference between them is just a single bit. So that's one of the cool applications and that would never happen in a spacecraft, because you literally lose millions of dollars of material. So this is how transistor without the gate voltage looks like. Okay. Okay, this is just the general description, but let's see if they have a diagram for the single latch. What they are talking about here is the leakage current caused by, okay, this is good. So, say for example, if a particle is hitting here, it's called single event transistor. How the transistor would overcome that and what kind of effects it would have that are being defined here. That's about it. If anyone has any other questions, also I would like to show you one more thing. So yeah, thank you. And at Astra, as we like to say in the astrophysics community, let's just look at one of the recent. Just a second. In the meantime, if anyone has any questions, please feel free